We discussed connecting batteries in series to enhance the terminal voltage. If we want to enhance the terminal current, then we can connect batteries in parallel. But can we connect batteries in parallel is the question. Now let us say that we have few batteries connected like this in parallel. We have the terminal voltage Vt, and you have the IB1, IB2, IBN currents from each of the battery, and the terminal current IT is sum of IB1 plus IB2 plus IBN, so on. So this will increase the discharge current capability of the whole set, of the whole system. However, you should note that one cannot connect voltage sources in parallel. We have seen that earlier. Connecting voltage sources in parallel will cause huge circulating current to flow among them, even if there is a small difference in the voltage, even in nanovolts or microvolts. There can be a huge circulating current because their impedances, the series impedances of the sources are almost zero, and then there can be a huge circulating current. And this will lead to huge reduction in the capacity of the whole battery set. So in general, you don't directly connect two voltage sources in parallel like this. This is not on. In order to avoid the circulating current problem, I could connect diode in series with each of the battery and OR them and then connect it to the load like this. So in this case, there will not be a circulating current between these two batteries because of these two diodes, and the ORing effect will try to see that current from here and here flow through the load. But there is no guarantee that there will be sharing of current between the two batteries. It depends again upon the internal impedances of the two batteries. Let us say the internal impedance of this battery is less. So this will try to drive a large current. And if this has an internal impedance which is larger, then there will be a drop across the internal impedance, and then this diode may go reverse biased. So only this will be delivering power to R0. So these problems may occur, and you cannot guarantee or ensure the sharing of current between the parallel connection. Then this defeats the purpose of having enhanced terminal current. So what do? We need to have some electronics come into the picture. Let us have a look at that. Let us now discuss how we will go about connecting batteries in parallel to a PV application. A typical PV application is like this. The PV module is connected to a buffer capacitance CT like this, and then which is connected to R0. When you have a battery, you are normally connecting the battery here across these terminals, but you can connect only one battery, a single battery. If you are having many batteries and you want to parallel them such that the terminal current is enhanced, then we will have to take the aid of DC-DC converter. So let us say that I have a battery here. Now this battery, I want to interface it to this point. How will I do that? So this battery, let me pass it through a DC-DC converter. I will take a boost converter as an example, but you can take any other converter too that will match this battery potential with the terminal potential of the PV panel, where you can appropriately take the duty cycle, which we have discussed earlier. It need not be just a boost converter or a buck converter or a buck boost converter. It can also be an isolated converter like a flyback converter. Probably I will show you an example later. Now let us say that this is the first part of the boost converter. You have the inductor and the switch, and I should have a diode here. Let me make these two grounds common. So let's say this is the same circuit ground, and here we will put the diode. The boost converter circuit now becomes complete, and the diode output should go to a capacitance, and that capacitance will be the capacitance CT. So the boost converter will pump the voltage from here, boosts it, and then puts it into the capacitance CT. So when the transistor switch is on, the energy, the power is flowing through in this fashion, current is flowing through, and the energy is stored in the inductor. And when the switch is off, the current of the inductor will flow through this diode into the CT and then back again. So this will be how it flows. Now that will be one battery connected in this fashion. Now let us say you have another battery, and let me include one more converter. I'll put the boost converter similarly, and battery will pump. When the switch is on, the battery will charge up the inductor, and the switch is off, it will flow through a diode like this and to the capacitor here. So in this way, this battery, let me say it is VB2, will pump the power from the battery into the capacitor CT. Now these two are operating independently, and therefore there will be ORing of power, and therefore the current will be enhanced. Now the point here to be noted is that these two batteries need not necessarily be of the same voltage. This could be a 6-volt battery, this could be a 12-volt battery, and this could be a 20-volt DC bus at the terminals. So accordingly, depending upon the duty cycle, you can still pump energy into the CT in parallel. So that is the advantage of using a DC-DC converter. You could also, as I said, use an isolated converter. Now let us say I have a battery connected in this fashion. It's the same ground. Now I have this battery. Now this battery is VB3. Now that is connected through an inductor and the switch. So when the switch is on, energy is stored in the inductor. Now I will pass it on to the secondary side of the inductor in this fashion. So when the switch is off, so when the switch is on, dot is positive. When the switch is off, the dot becomes negative, non-dot becomes positive, this becomes positive. This will start pumping the current to this node into the CT, and then it will come back here, secondary of the capacitor, secondary of the transformer. So you will see that you can pump energy from this battery into this buffer capacitor CT, even from a non-isolated converter. So it is not necessary that you should have same converter, same battery. You can have different batteries, a eutectic combination of the batteries. You can have different converters and different types of converters, isolated, non-isolated, and still pump power into the bus capacitor in parallel. One shortcoming of this, what I have just shown, is that power can flow only in one direction power flow. What it means is that power can flow only from battery to CT, VB1 to CT, VB2 to CT. Power cannot go from CT to back VB1, VB2, because when you normally connect a battery here, if there is any charge that has to be removed, that can sink into the battery can act as a sink. But here with this, because of the presence of these diodes, they can only source and they cannot sink. And let's say even the PV panel is having an internal diode, protection diode, and therefore this also cannot sink. So what will happen if you need to discharge the capacitance CT? So you have no sink current capability. Now let us say that this R0 is removed, that is, it is open circuited. R0 is infinite. So if R0 is infinite, and let us say CT is overcharged. If CT is overcharged, this voltage is more than needed. You need to discharge the CT. How do you discharge the CT? The CT has no discharge path. It cannot discharge through this, it cannot discharge through this, it cannot discharge through this, it cannot discharge through the PV, because PV is having a protection, series protection diode. So therefore CT cannot be discharged at all, and it doesn't have a discharge path. This is the one single drawback of this particular topology that I have drawn, but we will try to alleviate this problem. We will see how we can remove this problem, and we will try to answer the question how to discharge the CT if it is overcharged under the condition of R naught infinity, or even during any other conditions where you need to remove charge from the CT. Let us now see how we can solve the problem of unidirectional power flow. We will make the power converters bidirectional. So first let me connect the PV source to the buffer capacitance which is connected to the load. This is CT. Now to this CT we need to set up the interface for connecting the battery. Now consider a battery, and like as before we will have a boost converter, and I will common this ground, and I'll make this ground also same points. From here diode up, straight up. So let me connect the diode. So now this portion is the boost converter. When the switch is on, energy is stored into the inductor. When the switch is off, energy stored in the inductor is dumped into the capacitor CT and back. Now how do we pump power back into the battery in case there is excess charge on CT, either due to regeneration or due to regeneration back from the load? So what we shall do is make a connection like this. Now I'm connecting a BJT here, BJT or a MOSFET like this, and across this transistor a diode. I'm connecting a BJT across this diode, and I'm connecting a diode across this transistor. Now you see, now assume that this is the input source and power has to flow in this fashion to the battery. So if you look at that, you look at only the red components: BJT, diode, inductor, battery. So this forms a buck converter in this direction. It forms a boost converter in this direction. Battery to CT, when the power is flowing in that direction, then it is boost operation. It is the blue components. CT to the battery, we use the red components, and it will be buck operation. So it will become a buck converter. So in this way, if we use this technique, then you can have power flow in both direction, to and fro, and you will not have the sourcing sinking problem. So we will call this as enable sourcing. So when you enable this and allow the gating pulses to come into this base drive of this BJT, this transistor is switching, enabled, and the battery is able to source. You will have this pin also, and we will call that one as enable syncing. So these two are mutually exclusive. When you enable syncing, then this transistor is switching on and off at high frequency, and the buck operation comes into the picture, and the power is delivered into the battery from the CT into the battery. So this way you can pump power in both the directions. So now let us mark off this portion. So this is our main interface block between the battery and the PV terminal, and this is called the interface block for parallel connection. Now this interface block you can duplicate. So let us say I have one more interface block like this, and I connect a battery. I make this ground connection here, and then I bring out this enable sourcing pin out. Then I bring out this enable syncing pin out, and then after that I'll connect this as the interface block. I will connect that. So in this way one more battery is interfaced to the CT in parallel. Now if I call this VB1 and I will call this one VBN, and in between there can be any number of blocks, any number of batteries, and then there can be any number of such interface connections in parallel to this terminal voltage point to enhance the terminal current. VB1 to VBN may be same batteries, or they may be different batteries or different types of batteries. One could be lead acid battery, one could be lithium polymer battery, one could have high power density, one could have high energy density. So you can have a eutectic combination of batteries trying to get connected in parallel and delivering appropriate power. These interface blocks, which are basically DC-DC converters, which could be boost, buck boost, or flyback converters, enable this interface to happen. And by using this kind of bidirectional switches, you will be able to make power flow from this direction to CT and from CT to this direction. So now let us say that you are going to source. You will be enabling this, you will make this 0, you will not allow this transistor to switch, only the diode will be used. So as this is switching, power from here is put into the CT. Now once the CT voltage goes high beyond a particular set specified limit, then we would like to put it into the battery. So you can enable the syncing mode. This can be enabled, this will be disabled. So only the diode of this red component diode and this BJT will be used, and the bucking operation will happen, and then the power will be put into the battery in this fashion. We shall now see how we will get the signals. Consider the voltage across CT. Let me draw that as VT. Is the terminal voltage. Now using this terminal voltage, let us decide whether we can give the signal for enabling sourcing or enabling syncing. Now let me draw a comparator, and the output of the comparator, comparator output will give a gate signal, and I will AND it with an AND gate, and other input to the AND gate I will give it to a clock, and the clock will have duty cycle pulses like this, which will actually pass on the pulses to the switch based drive. Likewise, I will have one more comparator, and the output of that comparator goes to another AND gate. It gates another AND gate input, and the clock is given there. So here you will get gated clock pulses in these two places. Now I will connect the inputs like this. Okay, now the first input here I will call it as VT max. This is something that we need to set. We will say that the voltage across this capacitor cannot exceed VT max. That is the upper limit. And the other one is the sensed value of VT. We will give it to this pin. And I'll say that is plus, and minus. So let us complete the naming of the parts. Call this one as enable sourcing, call this one as enable syncing. You have the supplies. Yeah, the operation is pretty simple. Vt is the sensed signal. Vt max is a constant. So whenever Vt is less than Vt max, this is high. And here Vt max given to the minus terminal, minus pin. So this is low. So this is high when Vt is less than Vt max, and this AND gate is enabled, this AND gate is not enabled. So clock pulses pass on to enable sourcing. So this will be pulsing and this will act as a boost converter. So that is why power will flow from here to CT. Now when Vt crosses Vt max, Vt becomes higher than Vt max, Vt is connected to minus here, this will go low. Vt is connected to plus here, this will go high. Moment this goes high, this AND gate is enabled, this is disabled. So enable syncing, clock pulses go into enable syncing. It will go here and this will start switching, this will not switch, and therefore this will now act as a buck converter and power flows from Vt side into VB1. So in this way you can have power flowing both back and forth, and just by sensing Vt you can have a measure of regulation of the voltage across CT, and the batteries, as many batteries as you wish, can be paralleled in this fashion.